Hi everyone. In this video we're going to talk a little bit about Taylor series, where we're going to find how to figure out from a given function how to write it as a power series and try to figure out the coefficients of the power series from the function. Okay, so we're going to go through a few examples and see how it works. But first, um, let's consider a function given by a power series, and this power series is going to be centered at x equals c for the center, right? So f of x is written as a series of certain coefficients, certain numbers, times powers of x minus c, right? X here is our variable. And the question is how to find the coefficients of this power series in terms of the function f of x, right? So maybe you know the function f of x, f of x maybe is equal to e to the x, or f of x is equal to sine of x. So you know the function and you would like to know what is the power series that this function can be written by. Not all functions can be written as power series, but a lot of the functions that we know. Um, so usually when you start with a function and you try to write it as a power series, we call that power series the Taylor series of this function. That's why we're saying a Taylor series. Okay. So if you have a function and you write its power series, that's what's called the Taylor series of that function. And the idea is how can we find the coefficients, all right, in terms of the function that we have, all right? So let's start thinking a little bit about that problem. So the a0 coefficient, the constant term, is very easy to find. Okay, so you write f of x as your power series, right? So this is from this formula here, a0 plus a1 x minus c plus a2 x minus c squared, right? It goes infinite till infinity. And what you do is you can plug in x equals c on this equation. So on the left side, you get f of c, right? X equals c. And on the right side, you get a0 plus a1 of c minus c plus a2 of c minus c squared. But when you plug in x equals c on the right side, all of these x minus c terms become 0, right? So really the equation that we're left with is that f of c is equal to a0. And so there you go. You found the a0 coefficient from your function f of x. If you know what f of x is, then you can figure out the first coefficient of the power series, of its Taylor series, by plugging in the center into the function f. Okay. Well, what about the other ones? What about a1, a2, a3? How can we figure those out? So there's a theorem that will really help us out uh, to do exactly that. So the theorem says the following. If we have a power series, f of x equal to this power series, right? Polynomial of infinite degree. If this power series has radius of convergence r, then it is differentiable. It has a derivative along its interval of convergence, and you can write the power series for its derivative. So its derivative is also going to have a power series expansion, and it's just obtained by taking the derivative term by term of this power series for f, right? So if here you take a0, you take a derivative, that's just a number, so it's 0 there. So that's why this is starting at n equals 1, because the a0 term here, once you take the derivative, that's 0. The a1 term is a1 times x minus c to the 1. And when you take a derivative, you just get a1. Um, a2 x minus c to the 2, you take a derivative, the 2 comes down, you get 2a2 x minus c to the 1. So that's where this formula comes from. If you take a derivative of an x minus c to the n comes down, so it's nan, and the exponent there gets subtracted by 1, right? X minus c to the n minus 1. So the main thing to know here is that if your function is given by a power series, then it is differentiable, and the derivative um, has a very similar power series expansion. You just take derivative term by term. It will have the same radius of convergence. I don't know if I said that. Yeah, in any case, the power series here will have exactly the same radius of convergence as the previous power series. Um, and it has this formula. If you decide to re-index, so call n equals n plus 1 so that n starts at 0, then it has this formula, Right? So sometimes this is useful. It's not really going to be very important for us. The good thing is that the x minus c is raised to the n now instead of the n minus 1. So it looks a little nicer, but not super important, the re-indexing. So let's see how we can use this theorem to figure out, if we know the function f of x, how we can figure out the coefficients of its Taylor series. Right? So how to find a1. Right? So we figure out already how to find the a0. So if you have a power series, again, like this, to figure out the a0 coefficient, you just need to plug in c into the function. Right? So a0 is f of c. Now, if you want to figure out a1, you take your power series, you write it out. Okay, a0. All right. So a0 we already figured out. That was f of c. Right? Now, you can take a derivative of this function, right? F prime of x. You just take derivatives term by term. So the a0 is going to disappear because derivative of a constant is 0. Derivative of this is going to be a1. Derivative of this term is going to be 2a2 x minus c. The derivative of this term is 3a3 x minus c squared. The next one would be this 4a4. Now, what we can do is plug in c, x equals c, into the derivative. Right, so here if we plug in x equals c, all of these terms become 0, right? So if you plug in x equals c into this equation, on the right side, all of these terms become 0. We're just left with a1. And on the left side, you have f prime of c, right? And so we find that a1 is equal to f prime of c. Right, so we figure out a0, figure out a1. What about a2? We do this again. We take another derivative. So f prime prime, you can also compute the power series. Just take derivative term by terms of the first derivative. Right? Derivative of a1 is going to be 0. Derivative of 2a2 x minus c will be 2a2. The derivative of 3a3 x minus c squared will be 3 times the 2 that comes down, a3 x minus c. 4 times 3 that comes down, a4 x minus c squared. Right? So this is the power series for the second derivative. Again, we plug in x equals c. Plug in x equals c. On the right side, everything becomes 0. So let's see. So first, the left will be f prime prime of c. And on the right is 2a2. And then all of these terms are 0. Right? So we get that a2 is f prime prime of c divided by 2. That's the second coefficient. What about the third? Take another derivative, f prime 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 of x. This term goes to 0. Taking a derivative of this term, you get the 3 to a3. Taking a derivative of this term, you get 4, 3. The 2 comes down, 2a4. Right? X minus c. The next term is 5, 4, 3, a5, x minus c squared. Plugging in x equals c again. Plug in x equals c. On the left, we see f prime 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 of c. And on the right, we see 3 times 2 times a3. All the other terms are 0. Let me scooch this a3 a little bit. So we find that a3 is equal to f prime 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 of c divided by 3 times 2, which is the same as dividing by 3 factorial. Right? 3 factorial is 3 times 2 times 1. So it's the same as 3 times 2. Right? So we get that formula. And in general, you can keep doing this, and what we find is that the an coefficient, right? For example, if you take another derivative, you're going to see that f, the fourth derivative of f plugged in as c, will be equal to 4 times 3 times 2 times a4, which is 4 factorial times a4, right? So the an, in general, will have the formula f n, and this means take n derivatives, plug in x equals c, and divide by n factorial. Right? So let me write here what that means. This means nth derivative. When you write the n in the parentheses like that, that's what it means. Right? So this matches our previous formula. So a0 is f of c with no derivative. That's f of 0 in the previous formula. So it's f of 0 of c divided by 0 factorial, which is 1. So this is f of 1. So first derivative, plug in c divided by 1 factorial. Second derivative, plug in c divided by 2 factorial. 2 factorial is equal to 2. Third derivative, plugged in c divided by 3 factorial. Right? So it always follows this pattern. And you just obtain that by following this process that I explained. Okay, so this is the formula for the nth coefficient, right, of the Taylor series. Nth coefficient of the Taylor series. Okay, so, and again, I'm using the name Taylor series because it's a pretty common name and it's good that you know what it means. But it just means the power series of the function, right? So if you have a function, not all functions can be written as a power series, but when it can be written as a power series, you call the power series the Taylor series of this function. Okay? And in fact, there's this silly thing that I really never use, but it's good to know. There's this name also of a I don't even remember how to write it, but I think it's Maclaurin series. A Maclaurin series is just a Taylor series when the center is equal to 0. So if you're centered at 0, some people call it a Maclaurin series. I find it a little bit silly to give a different name to such a similar thing. So Maclaurin series, people don't I don't see this name very often, only in calculus books basically. But Taylor series, it is something that people use a lot in different books as you keep going, in college and stuff. You will probably hear more about Taylor series. It's just a power series of a function. All right. So let's go through some examples. Let's find the Taylor series for f of x equals e to the x centered at x equals 0. Okay. So that would be a Maclaurin series if you use this name because it's centered at 0, right? But it's very common to just call it a Taylor series. All right, so first we compute the derivatives. We're going to use this formula to compute the coefficients, right? So to find the Taylor series, basically all you need to figure out is what are the coefficients, right? Because I already told you what the center is. So to figure out these coefficients, you need to figure out the derivatives of your function, right? You're going to have to plug in c into the derivatives of your function. So first thing is figure out the derivatives of f of x equals e to the x. Well, that's pretty easy. F of x is e to the x, f prime is e to the x, f prime prime is e to the x, right? E to the x, you can take a derivative and nothing really happens to it. So the nth derivative of f of x is just e to the x. It's always e to the x. The coefficients of the Taylor series are an is you plug in the center is 0, plug in the center into the nth derivative, divide by n factorial. The nth derivative is e to the x. That's the nth derivative. Plug in 0. That's e to the 0 over n factorial. So that's 1 over n factorial. These are the coefficients of the power series of e to the x, right? The Taylor series for e to the x. So we have that e to the x is a sum for n equals 0 to infinity of x to the n multiplied by 1 over n factorial, which is that. So remember, I said in class that this is the Taylor series or the power series for e to the x. That's how you derive it, right? All right, let's do one more example. Let's find the Taylor series for the function f of x equals ln of x centered at x equals 1. Ln of x is a really good example to talk about a function that should be centered at a different center, not at 0, Because if you think about the graph of ln, right, it looks like this. So you can't center your power series at 0. Your function is not even defined at 0. Right? So usually we need to center at a different point. A pretty common point is centering at x equals 1. All right. So first thing to do, we're going to apply our formula for the coefficients of the Taylor series. So we're going to need the nth derivative, a formula for the nth derivative of log. Right? All right, so derivatives of log. Well, f of x is log. The first derivative is 1 over x, right? Take a derivative of log is 1 over x. The second derivative, you take a derivative of 1 over x, that's minus 1 over x squared. Right? It's just a power rule. This is x to the negative 1. The negative 1 comes down and becomes x to the negative 2. And here, you take the third derivative, you take a derivative of here, of this function. Again, it's a power rule. X to the negative 2, the negative 2 comes down with this negative 1. It turns into a 2. And it becomes x to the negative 3, which is this over x cubed. Okay, here again, you take one more derivative. The negative 3 comes down, so you get negative 3 times 2 over x to the 4. Take another derivative, the negative 4 comes down, so it's 4 times 3 times 2 over x to the 5. And you see a pattern here. Okay, so dot, dot, dot. The pattern is what? The nth derivative. So for n equals 0, the 0th derivative is the original function. It looks pretty different, right? All of these look like 1 over x to the something, but the original function doesn't really fit this prescription. So I'll give you a formula for the nth derivative for n greater than 0. It won't work for n equals 0. But what is the formula? You see that the signs are changing. For f prime, it's positive. F prime prime, it's negative. F prime prime prime, it's positive. The fourth derivative is negative. Fifth is positive. So the first thing is I'll put a negative 1 to the n plus 1. In that way, this is positive when n is even. And it's positive when n is odd, right? So 1, 3, 5, because then this is going to be an even number, and then negative 1 to an even number, that's positive 1, right? And it's going to be negative when n is even, right? When n is even, then this thing is odd. N plus 1 is odd. Negative 1 to an odd number is negative 1. So this takes care of this, the way that the sign is changing, right? It's positive on the first derivative, negative on the second, positive on the third, negative on the fourth. This takes care of that. Then you see on the top, on the numerator, it's always a factorial. This is 2 factorial, 3 factorial, 4 factorial. So it's, and the number of derivatives is, here is 5, so it starts at 4. Here it's 4 and it starts at 3. So what you see here is if you took n derivatives, you're going to see an n minus 1 factorial, right? That's why this 5, you see a 4 factorial. This 4, you see a 3 factorial. And then finally, you divide it by x to the n, right? So fifth derivative, x to the 5. Fourth derivative, x to the 4. So this is the formula for the nth derivative of log, sorry, of log of x, right? This is the formula. The coefficients of the Taylor series, a0, it's not going to fit into this formula, right? This formula only works for n greater than 0. A0, you plug in the center, our center is 1, into your function f. The function is ln of x, so this is ln of 1, which is 0. Right, so a0 is 0. And for n greater than 0, an, you plug in the center into the nth derivative, and you divide by n factorial. Well, here we're going to need to use our formula for the nth derivative of log. This is going to look like, I'm going to zoom in a little bit. It's going to be negative 1 to the n plus 1 times n minus 1 factorial divided by x to the n, but x is 1. So 1 to the n, all of it divided by n factorial. Now I can zoom out again. Okay, so here what do we have? We have the negative 1 to the n plus 1. And n minus 1 factorial divided by n factorial is just n, right? That's because I'll write it here. N minus 1 factorial divided by n factorial. Well, n factorial is n times n minus 1 factorial. So these things cancel. You get a 1 over n. That's where that comes from. So, okay, hopefully it's clear. Basically what I was doing is saying, like 3 factorial, I'm going to write it here, and then 3 factorial over 4 factorial. What is that? 3 factorial is 3, 2 times 1. 4 factorial is 4 times 3 times 2 times 1. But this bit is exactly the same as that bit. So you get a 1 over 4. That's the same thing here. N minus 1 factorial over n factorial is always 1 over n. All right. So that's the coefficient of the power series, negative 1 to the n plus 1 over n. So the Taylor series expansion is, well, series. Now, instead of starting at n equals 0, because the a0 term is 0, I'm not even going to write it. I'll start at 1 to infinity, negative 1 to the n plus 1. The center is 1, let's not forget that, times x minus 1 to the n divided by n. So you can divide the whole thing by n, I guess. Doesn't quite matter how you write it. Okay, that's the Taylor expansion for log of x centered at 1. All right, one last example. Let's find the Taylor series for f of x equals cosine centered at x equals 0. So I guess you can call this a Maclaurin series because it's centered at 0. Okay. Solution. First, compute the derivatives of cosine. So f of x is cosine. First derivative is negative sine. Second derivative, you take a derivative of negative sine. It's negative cosine. Third derivative here, it's negative sine with a negative positive sine. Positive cosine. It goes like that. The thing is, once you take a derivative of sine here, the fourth derivative is cosine. It's the same as your original function. And the fifth derivative would be negative sine, which is the same as the derivative. So it's going to start repeating, right? It's cosine, negative cosine, sine, cosine, negative cosine, sine. Is going to keep repeating like that in cycles of 4, right? So they start repeating. If you plug in, we're not going to need the actual derivative. We just need the derivative plugged in at the center, right? So let's plug in the center x equals 0 into these derivatives. Right? F of 0 is cosine of 0, that's 1. F prime of 0 is negative sine of 0, but sine of 0 is 0. Okay. F prime prime of 0 is negative cosine of 0. Cosine of 0 is 1, so that's negative 1. F prime 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 of 0 is sine of 0, which is 0. Fourth derivative of f at 0, it's cosine of 0, 1. Fifth derivative of f at 0 is negative sine of 0, which is 0. So you see that it repeats like that. 1, 0, negative 1, 0, 1, 0, negative 1, 0. Okay. Well, in order to find the coefficients, we need to consider separate cases. You see that the even derivatives look quite different than the odd. The odd derivatives are all 0, right? At 0. So we break down into cases. If n is even, then we can write n as 2 times some number, some positive integer, right? And so we write what is a of an even number n, right? So a2k here. You're going to take f2k of 0 divided by 2k factorial, right? So this is just 2k is equal to n, right? So an is the nth derivative divided by n factorial, but n is equal to 2k now because we're assuming n is an even number. All right, what is this going to look like? For the even derivatives, you see it alternates 1, negative 1, 1, -1, right? It just keeps alternating. The correct thing to put on the top here is -1 to the k, right? Because then when k is equal to 0, you're going to look at a0 or f of f0, you get a +1, right? So -1 to the 0 is +1. Now when k is equal to 1, so here you're going to be looking at the second derivative. 2 times 1 is 2, right? On the second derivative, it's negative. So -1 to the 1, it's negative. So it's good, right? So this is k equals 0, k equals 1, k equals 2, k equals 3. When k is even, it's positive. When k is odd, it's negative, right? So that's why -1 to the k is the correct thing to put there, divided by 2k factorial. Nothing to do there, right? So that's the formula for the even coefficients. Now if n is odd, so you can write it as an even number plus 1, right? So something multiple of 2 plus 1. But for odd coefficients, you see that these odd derivatives, they are all 0, right? When you plug in x equals 0. So this is 0 over 2k plus 1 factorial, which is 0. Right? So the even coefficients have this formula. The odd coefficients are all 0. So we figure out all the coefficients of the Taylor series. How to write it, the thing here is you don't want to write a series on n here, like n from 0 to infinity, because almost the ANs, half of them are 0, right? A1, A3, A5, A7, all of those are 0. All the odd ones are 0. So you're going to write a bunch of things that should be 0 there. It's not really a good move. So the best thing to do is, instead of summing on the n, the index n, to sum on the index k. K equals 0 to infinity, and only write the even terms, right? So a2k, oops, I wrote x by accident. A2k, oh, the center is 0, so a2k x to the 2k, right? This is still correct. We're only writing the even terms, but that's okay because there are only even terms. All the odd ones are 0, right? And then if we use our formula for the even coefficients, we find that cosine is the sum for k equals 0 to infinity of -1 to the k times x to the 2k divided by 2k factorial. All right? So if you write this out a little bit, k equals 0, you're going to get 1. K equals 1, you get negative x squared over 2 factorial, 2. K equals 2, you get plus x to the 4 over k equals 2 here is 4 factorial. And it goes like that. Minus k equals 3, it would be x to the 6 over 6 factorial plus x to the 8 over 8 factorial, da 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 da, forever. All right? So this is how you find the Taylor series of a function. You need to basically use the derivatives of this function to compute what the coefficients are. The most important part of what I told you in this video is basically this formula right here for the coefficients of the Taylor series, right? You can use it to compute Taylor series of a bunch of different functions. And we could also compute, which we have done, I believe, in class. You can compute the radius. Once you compute what the Taylor series is, you can compute what the radius of convergence of that power series is to know for which values of x that power series expansion is valid, you know. But that's it for this video. I'll see you guys in class to work on the mock final. All right, see you later.